let's switch over to VS Code. And so here I'm looking at the file in data p-adics called p-adic-norm.lean. We'll flip through a few files, not everything in this directory though. So in this file, we define the p-adic norm. As the header says, we define the valuation in the norm, give some basic information about it. So we start with the definition p-adic val_rat. It can be a little hard to read because of this multiplicity function. This wasn't quite how we wrote it informally, but let's see what the tooltip for multiplicity says. Multiplicity AB gives the largest natural number n such that a to the n divides b. Oh, good. That's exactly what we want. The complication is that this gives us an enat. So that's a natural number or infinity. This is to handle the zero case. So we need to do a little bit of work to show that we don't actually hit the zero case. But that's fine. And for our purposes, we're going to take the value 0 in the case q equals 0 or the case p equals 1. So yeah, so that's our rational valuation. Notice that we actually skipped the integer valuation. The subtraction, the numerator minus denominator, was built into the definition here from the beginning. So then there's a whole bunch of library development. Whenever we're defining something in Lean, we tend to build up an API around it. So we've defined what the valuation is. Now we have to prove what's the valuation of a negative thing. What's the valuation of 1? What if I cast an integer into a rational number and try to take the valuation of that, and so on. There's a whole big API to build up here. We're not going to read through all of this. I'm looking for what I believe is around here. There we go, the p-adic norm. We define the valuation. At that point, defining the norm is easy. If the input is 0, the norm should be 0. Otherwise, we should take p to the power of the negative valuation. That's 1 over p to the power of the valuation. Exactly as we put it on the slides. We should note that to define the valuation, we didn't actually assume that p was prime. Similarly, to define the norm here, there's no assumption that p is prime. We've only included the prime p hypothesis for the lemmas in which we actually need it. If we scroll up, we can see this in some places. So this lemma, p-adic val nat primes, details are not important. If p and q are non-equal and are prime, then their valuation is 0. Well, there we definitely need the assumption that that p is prime. Here again, you have to assume that p is prime in order to make this lemma true. So the prime assumption is not needed for everything that we're doing at this point, but Lean conveniently makes it very clear to us when it is actually assumed. This is one of the benefits of using a proof assistant. This doesn't really get swept under the rug. But okay, we've defined the p-adic norm, and again, we go through the process of building an API. The p-adic norm is non-negative. The norm of 0 is 0. The norm of 1 is 1, and so on and so on. What about the p-adic norm of p? Well, that's strictly less than 1. Yeah, we can keep going. Fairly big API here. This is not a short file. Here's a nice thing. Here we show that the p-adic norm on the rationals for now is non-Archimedean. The norm of q plus r is at most the maximum of the norm of p and the norm of r. Remember, this is a stronger property than a typical absolute value has. Yeah, so we keep going, and here, this is useful. Remember that when we defined Cauchy sequences, we had this is absolute value predicate. Said our function was non-negative, additive, multiplicative, etc. Here we instantiate the fact that the p-adic norm is actually an absolute value. And that's the end of this file. We've defined the p-adic norm. But remember, we did the whole completion process very generically. We had an API for that as well. We said plug in the absolute value, and we get given a new type, the completion, for free. And that's what we're going to see active very soon. There's a little bit of work first. We actually do need some results about Cauchy sequences of p-adic numbers, which is what we're looking at here. This type p-adic seq is just Cauchy sequences of rationals with respect to the p-adic norm. Where exactly in this file do we want to be? There we go. There we go. The p-adic numbers, if we assume that p is prime, then we take the Cauchy sequence completion with respect to the p-adic norm p. So that's easy enough, actually. To write this down, we didn't need any of the previous 400 lines. And we give ourselves some nice notation for it. Even better, we're going to instantiate this as a field. We want to say that if I have p-adic numbers, I can add them, multiply them, divide them. That comes completely for free from the Cauchy sequence construction. No extra work at all. Again, none of the previous 400 lines really matter for this one. So the generic construction is really powerful for us. And then there's a lot of API to set up. Those first 400 lines are actually mostly involved in this, in lifting the p-adic norm from rational numbers to Cauchy sequences of rationals to p-adic numbers itself. We want to show that we actually have a norm function on the p-adics. Then otherwise, all of this file is really establishing various facts, some of which we saw in the slides. It has a norm, it's a normed field. At some point we'll have shown that the norm is non-Archimedean. I don't know exactly where that is. Yeah, this is 1,000 lines that give us probably not a complete API about the p-adic numbers, but for the time being, to prove Hensel's lemma at the very least, it's the machinery that we need. So I'm not going to go carefully through the p-adic integers file, but here we carve out that there's definition. Right, we carve out the subtype of p-adic numbers whose norm is at most 1, and we'll show that this is in fact a ring. And then finally, one more file, we prove Hensel's lemma. So this is a somewhat intricate proof. There's a lot of private things that are really not needed until the end. But at the very end of the file, we can state Hensel's lemma. It says, given some preconditions stated above, there is a p-adic integer such that if we take our polynomial f and evaluate it at z, we get 0. So z is a root of the polynomial f, and some other properties about z hold. We don't need to go into details about that for now. So all in all, we have a few thousand lines of code. Not all of it is really needed even to prove Hensel's lemma. We don't need everything about the p-adic integers. to get to this point here. But it's, again, we show this to you not for the exact statement of Hensel's lemma, but as evidence, constructive proof that, that real mathematics is formalizable in Lie. Yeah, so I hope that this has been interesting and not completely confusing with mathematics that you don't know. There's a whole world to be formalized, and this is a tiny, tiny piece of it. But yeah, there's plenty more to do, and maybe a few of you are interested in doing some. So thank you very much for listening.